The next topic here is about injective functions. Sometimes instead of using the word injective, I will be using the words one-to-one. So injective and one-to-one are identical terms. They mean the same thing. Now, how do we know that a function is one-to-one or injective? Well, the definition is written over here. If f of x1 equals f of x2, then the x1 has to equal to the x2. So basically, if you have two y-coordinates that are equal, then they must have come from the same x-coordinate, basically. Okay, now that is a nice and whatever definition, but we prefer one that we can work with. And the one that we're going to be working with is basically that one. Or sometimes we like to kind of think about, well, what does it mean to not be a one-to-one function? Sometimes it's easier to distinguish and find whether something is not one-to-one. So how do you know that something is not one-to-one? You will need the second definition that's written basically over here. So we said that a function f going from the set x to the set y, we say that it's not one-to-one if and only if the following is true. There exists an element x1 and x2 that have the same image, f of x1 equals to f of x2, but x1 and x2 are not identical. So basically, if you want to fail the test, if you want a function that is not one-to-one, all you have to do is basically come up with an example where two numbers in your domain have the same image in the codomain. That would be an example of a function that is not one-to-one, because it defies the rule. So the rule is, if you want to be one-to-one, every single y should have one arrow pointing to it. And if it doesn't, if it has two arrows pointing to it, the numbers on the other side better be identical. In this case, a and b are not identical, so this means that this example that I gave you over here is an example of a function that is not one-to-one. Okay, so it's a little bit confusing, but take some time to absorb this definition. We need to know what the definition is, basically, okay? So let's give it a shot. We have example 2, which says, here's functions f and functions g. The function f goes from the real numbers to the real numbers, and the function g goes from the integers to the integers. So again, domain and codomain. And again, domain and codomain. So the rules for the function f of x is this. The function f of x takes your input x, which is what you're putting from the domain, and it multiplies it by 4 and then subtracts 1 to it. And that's basically what it does. However, on the other hand, the function g takes a number from your domain, in this case we're calling it n, and what it does to it is it squares it. And the question is, well, which one of these two is going to be one-to-one? And in part A, we're investigating the function f of x. Is it one-to-one? To say yes, we would have to do a proof. If you think it's a no, what you have to do is basically give me a y-coordinate that has two different pre-images. So think of a number in the codomain that has two pre-images. So two numbers over here in the domain and one in the codomain that map to the same thing. But, you know, unfortunately, you're going to have a hard time doing that because this function is one-to-one. So let's take a look at how we build a proof to show that f of x is one-to-one. So we're going to begin by saying proof, and in this case, I'm just proving that f of x is one-to-one, so I put it in the comment. I'm going to begin by first defining the function f of x. So let the function f be from the real numbers to the real numbers with the following equation for the function f of x. Again, remember, the domain and codomain matter. So if this is not written down, then, you know, points will be taken off because we don't know what your domain and codomains are. Now, what do we have to do to show that a function is one-to-one? We have to basically say, if f of x1 and f of x2 are equal, then the pre-images must have been equal. So in order to show that this function is one-to-one, I'm going to say this. And suppose that we have f of x1, well, let me use little f of x1, comma, f of x2 from the codomain. In this case, the codomain is basically the second r that's written. That's the r that I'm talking about. Suppose that we have two of those in the codomain, and suppose that they are equal, that f of x1 equal to f of x2. Now, what I have to do is basically break it down, take it further until I show that the x1 and the x2 are themselves equal. If I can prove that to you, if I can prove to you that f of x1 equal to f of x2 implies for sure that x1 is equal to x2, then I'm done. I have proven that the function is 1 to 1. Okay, let me try to do that. So what is f of x1? Well, the function f of x takes your number and multiplies it by 4 and subtracts 1. So that's the same. It's true for x1. What about f of x2? Again, the function f does the same thing to x2. So the same comes out for x2. All right, let's add 1 to both sides of this. If we did, we end up with 4x1 equal to 4x2. And if I divide by 4 on both sides, I get x1 equal to x2. Is there any other choice? No, no matter how you do the problem, no matter how you rearrange the numbers or the letters, you're always going to reach the conclusion that x1 is equal to x2. So that means that the function f of x is 1 to 1. Because if I start with two y coordinates that are equal, I'm going to reach the conclusion that those y coordinates came from two x coordinates that were also equal. So that proves that the function is injective. And that means we're basically finished with the proof. So we're just going to write down QED at the end, and that's basically it. Now, what about the function g of n? Is it 1 to 1 or not? Well, as a reminder, the function g is going from the integers to the integers. And what it does is that it takes the value that you start with and it squares it. Is that function going to be 1 to 1 or not? The answer is no, it's not going to be 1 to 1. And let me give you an example. I'm going to pick an element from the second set. For instance, I'm going to pick the number 4. And I'm going to think about what is the pre-image. In other terms, what number do you square to get 4 at the end? Well, there are two choices. There's a 2 and there's a negative 2. If you square 2, you get 4. If you square negative 2, you get also 4. So these two come from the domain, and they both have the same image in the codomain. So that means the function g of x has failed the test. So my counterexample is basically that. The number 2 and negative 2 both have the same image. So if I take two numbers in the codomain that are equal, they may not have come from the same x coordinate, right? Two different x coordinates will square to be at the end 4. So that means the function g of n is not 1 to 1. So that's one way to do it, is to provide a proof. Let me show you a proof similar to the one I developed in part 1 to show you how this fails. So again, one option is to write down a proof using counterexample, and one other option is to write down a proof that involves something like the one we did in part 1. And that's what I'm about to do now. So proof in this case, actually it's a disproof. I want to prove that g of n is not 1 to 1. Or in other terms, that it is not injective. So I'm going to start again by letting g of n be the function that goes from z to z again, with g of n equaling n squared. And I'm going to suppose, like I did in part 1, that there are two y coordinates, g of n1 and g of n2, that come from z. Which z am I talking about here? I'm talking about the z in the second location after the arrow. And I want to suppose that they are equal. So I'm grabbing two y coordinates in the codomain, and I'm making sure that they are equal. And the question is, well, do the pre-images have to be the same? Now, what does the function g do? It takes your n1 and it squares it. Same thing happens with n2 when you plug it into a function g. So all I'm doing here is by substitution, replacing gn1 with n1 squared and gn2 with n2 squared. Now, I would like to remove the square root. I would like to remove the square, so I have to write down some sort of a square root. But remember, when you do square roots, you have to have a plus or minus. So n1 on one hand is equal to positive n2, or there's a second choice that n1 could be possibly negative n2. So having two y coordinates does not mean that the images, the pre-images are identical. They could be, which is what's happening in the first box, but at the same time, the pre-images could be negatives of one another. Since there's no way for us to eliminate that second choice from happening, it could happen. We don't know that it's not happening. We cannot eliminate that choice. Then we can say that the function g is not one-to-one. So this means that the g of n is not one-to-one. So why did it fail? It failed because there were two choices, two boxes at the end, not a single one. If somehow we had a way to kill this one off, if we had a guarantee from the problem that the second one could not be true, then that would mean that the first box has to always be true, in which case we could say that the function is one-to-one. However, we cannot safely remove the second option. There is nothing in the problem that says you can eliminate it. So unfortunately for this problem, the g is not one-to-one.